Hey everybody, in this video we are going to learn about radioactive decay. A little bit of a history lesson for us. Radioactive decay was first noticed in the year 1896 when this feller by the name of Henry Becquerel discovered that uranium salts, when kept near pieces of photographic film, would cause a reaction on the photographic film just like light would. So what he concluded was that the uranium was emitting something to cause this reaction. So basically he had like pieces of photographic film wrapped in black paper with uranium next to it, and then he discovered that when he developed the film it looked as if light had been exposed to it. And so he made the conclusion that uranium was emitting something. A few years later, a married couple by the name of Marie and Pierre Curie further investigated this phenomenon, and they were the ones who named it radioactivity. By the way, Marie Curie was the first woman to win the Nobel Prize. She won the Nobel Prize for her work with radioactivity, and she actually ended up winning two, one in physics and one in chemistry. One way that you can characterize the radioactivity that's created from a radioactive element is by placing it in a block of lead, so you can kind of contain what's being emitted, and then have that emitted stuff pass through a magnetic field. So here's a magnetic field directed into the page. So we know what happens when things move through magnetic fields. If they're charged, then they're going to experience a magnetic force. If not, then they won't experience a magnetic force. And so when you do this, you notice from any radioactive element three distinctive results. You notice one thing that's emitted that moves to the left, the way that I've drawn this, one that moves to the right but in a shorter radius, and then a third which is not affected at all. And so you can do the right-hand rule for this magnetic field situation. If you've got something moving upwards, so thumb goes up, and a magnetic field directed into the page, then your middle finger would point to the left. So the thing moving to the left in blue would be something that's positively charged, and number two, which moves in the opposite direction, would be something that is negatively charged. So this is a way we can study radioactivity. So we can make the conclusion that there's three different things being emitted. And this cat by the name of Ernest Rutherford gave them names. He named them after the first three letters of the Greek alphabet: alpha, beta, and gamma. So let's kind of take each of those things in turn. Start at the very beginning. An alpha particle, remember the symbol for alpha, is essentially two protons and two neutrons, which basically makes it a helium nucleus. It's not a helium atom because there's no electrons associated with it. It's just the helium nucleus. So you may remember from the previous video, the stability table that we saw, that a helium nucleus is very stable. It's got a high binding energy per nucleon. So a picture may look something like that. And remember that there's two protons with no electrons, so that means it has a positive charge. So we can say it's got a charge of +2 times the elementary charge, or using chemistry notation, we just say it's got a +2 charge. We could symbolize it either with the letter alpha, or we can symbolize it like that, using atomic symbol. So the atomic number would be 2, the mass number would be 4, and that would give us the element helium. So for example, Americinium-241 will decay into Neptunium-237, and in the process it will emit an alpha particle. This is something that's happening in your smoke detector in your house. As a result, energy is going to be released as well. So this typically happens for heavy elements. Americinium is a fairly heavy element. And so if we kind of drew a schematic, kind of showing the sizes of what's happening here, we end up with a slightly smaller Neptunium nucleus and then a relatively tiny helium nucleus. And they're going to be moving apart because of all that extra energy. Most of that extra energy is going to be in the alpha particle, kinetic energy, and that's because momentum has to be conserved during this process. And so the mass times velocity for each of those guys would be equal. And so since the alpha particle has less mass, it would have a higher velocity. So it's just like any other thing where two things are pushing apart. And so the alpha particle goes flying away from the neptunium nucleus, and so that's why we see the alpha particle, quote-unquote, emitted. The next kind of radioactive decay is called beta decay. Through careful studies, we saw that it's negative. We can conclude that a beta particle is just a free electron. What's happening in beta decay is that a neutron, through some weird voodoo stuff, is changed into a proton, and an electron is formed as well. So it would look like this, and then there will be energy released as well. So the why behind that has to do with quarks and even more elementary particles, which we really can't get into. And so it's just something that kind of spontaneously can happen due to the way quarks interact with each other. The electron, of course, is very small, and therefore it's going to gain most of the energy, which means that it's going to be ejected from the nucleus. So it's not one of the electrons that orbit around the nucleus, it's a new electron, and basically it goes blazing out of there so fast that it doesn't affect the other electrons in the atom. So it's not one of the electrons that were already there, it's a new electron created as a neutron, turns into a proton plus that extra electron. So for example, carbon-14, which is radioactive, will decay into nitrogen and then emit an electron as a result. In order to make all the numbers work, we have to assign the electron as having an atomic number of -1. It's like the opposite of a proton, so we'd say it's got -1 protons. And then a mass number of 0. And that makes all the conservation laws work out. Now in some situations, you can have beta decay, where a proton decays into a neutron, so kind of like this. And this also creates an electron, but instead of it being an electron, it's actually a different kind of particle that has the same mass as an electron and the same charge, but the charge is positive. Keyword being positive. So it would be like a positive electron, which you might give the fancy name positron. The positron is actually the antiparticle of an electron, something we may get into later. And so really there's two kinds of beta decay. Oh, obviously energy is created as well. So there's two kinds of beta decay. We can say there's beta minus decay, which would create an electron, and then beta positive or beta plus decay, which would create a positron. And so notice that in both situations the total charge doesn't stay the same. A neutron has no charge, so a proton plus an electron has no charge. And in the second kind, a proton's got a positive charge. A neutron plus a positron has a positive charge. So one thing we should be noticing is that the charge doesn't change during one of these nuclear decays. So in the year 1930, people were doing careful experiments with beta decay, and they noticed that some of the energy that they were expecting to show up was missing. They also noticed that momentum wasn't being conserved. And so something was missing. And so this physicist by the name of Wolfgang Pauli suggested that there was another particle that was being created during beta decay. The properties of this particle would be that it would have to be electrically neutral, so that charge would still be conserved, and it would have to be less massive than an electron, which is kind of surprising because electrons are like super duper duper tiny. So this thing would have to be even less massive than an electron or possibly have a mass of 0. This was given a few names over time, but the name that kind of stuck with this particle was the neutrino, which is Italian for little neutral one, And that name was given to the particle by a guy by the name of Enrico Fermi, who was very important in the development of the atomic bomb. The symbol that we gave this was the Greek letter nu, which is kind of like a slanty V with a tail on the front of it. If you just draw a V, people would know what you mean. Because neutrinos are not charged and they're very, very small, they almost never interact with matter. They're very, very hard to detect. In fact, they weren't actually discovered until the 1950s. So about 20 years after we noticed that there was something else going on in beta decay. Their mass is not zero. They actually have a mass of about 1/millionth of the mass of an electron. But it is kind of important that the mass wasn't actually zero, for reasons we'll see later on. And so, to kind of fix what we said earlier about beta minus decay and beta plus decay, is we would have to add a neutrino to each of these. So that neutrino, that little tiny particle, carries away some of the energy in beta decay. The third kind of nuclear decay we need to know about is gamma decay. A gamma, remember well, you may not know the letter yet, but it kind of looks like a ribbon. But a gamma particle is really just a high-energy electromagnetic wave. It's created when a nucleus that has already undergone nuclear decay, it's like alpha or beta, loses a little bit more energy by creating an electromagnetic wave. So remember, that's like the highest energy electromagnetic waves on the spectrum. It's important to realize that this does not change the structure of the nucleus. It just makes it more stable by lowering its energy. So an example of beta decay, in a certain reaction, nuclear decay, molybdenum-99 will decay into technetium-99 plus an electron, and then a neutrino and some energy. So that would be like beta minus decay. Now, as a result of this, the technetium nucleus is not entirely stable. And so to denote that, we would put a little asterisk by it. And the asterisk means that it is quote-unquote excited. You just got too much energy and it wants to lose some of that energy. And the way that it loses it is by creating a wave. It creates an electromagnetic wave and loses some energy, which means it's now more stable. We're going to see this same process later on with not free electrons, but electrons in a nucleus, not a nucleus, in an atom, only they emit radiation with much lower energy. And so we'll see how we can create light and other electromagnetic waves from the electrons in an atom. This is an example of that process happening in the nucleus of the atom. And so because the energies involved are larger, the gamma wave created has a lot more energy. Okay, so let's next talk a little bit about how these things interact with matter. Alpha particles, because they're big, are very weakly penetrating. In fact, they'll barely go through a sheet of paper. So paper is all you need to protect yourself from alpha particles. The problem, however, is that they're highly ionizing due to their large +2 charge. So remember, ionizing means that an atom or molecule loses or gains charge. We'll talk about the effects of that here in a minute. A beta particle is moderately penetrating. Those electrons are smaller, move through more stuff. They can typically be stopped by something like aluminum foil. So you can protect yourself from beta radiation with aluminum foil in your pantry. They will ionize particles, but not as strongly as an alpha particle, because they have less charge. Gamma particles, gamma waves, are highly penetrating. In order to stop those, you need a couple centimeters of lead or several meters of concrete. So gamma waves will go through a lot of stuff. Because they're not charged, they don't ionize particles directly, but they can cause reactions which will cause other things to ionize. So they can indirectly cause ionization. So let's briefly review the idea of ionization. In chemistry, you learned that when atoms or molecules lose charge, lose lose electrons or gain electrons, then we call them ions. And so ionizing is just the process of causing a molecule or atom to become charged. This can damage living tissue, like your living tissue, by charging atoms or molecules that should not be charged. And then that can have two effects. That can cause harmful chemical reactions, or it can prevent useful chemical reactions from occurring. A real common example would be in cellular transportation, how stuff gets in and out of your cells. Even worse, it can break the bonds in your DNA. You might call that a mutation. Extensive damage to the DNA is an unwanted mutation. That's bad. And if it's not checked by your body's natural defense system, then that could grow and proliferate into something you would call a tumor. And so, excessive exposure to radioactive materials can lead to things like cancer. Cancer is bad. Cancer is just a mutation in your DNA, which can be caused by ionizing radiation. And so that's why these things may be somewhat dangerous, but typically not. So, what's conserved in nuclear reaction? First of all, mass is converted to energy. We knew that from last time. So we really can't use those conservation laws to figure out what's going on. Charge has to be conserved, however. Another way of saying that charge has to be conserved is that the atomic number stays constant. The other thing that has to be conserved is the number of nucleons. Remember, a nucleon is a proton or a neutron, and together they make up the mass number. And so the reason that we have the term mass number is because that number is not going to change during a nuclear decay process. And then the third thing to remember, mechanically speaking, is that momentum is conserved. So if we want to know how fast the particles are moving after a decay, we would use conservation momentum. So let's look at a couple of examples of how we can use those first two laws to predict the products by predicting the atomic number and the mass number. So for example, radon-226 will undergo alpha decay. And so we might write something like that. What we need to be able to do is predict the product that's formed. And so if we look at the numbers on the bottom, that will be the atomic number, that number's got to stay constant on both sides of the arrow. And so since radon starts with an atomic number of 88, the alpha particle's got an atomic number of 2, then our other product has to have an atomic number of 86. Same thing's got to be true of the top, the mass number. We go from a mass number of 226 to the alpha particle having a mass number of 4. That means there's 222 nucleons left over in our product. And so grabbing a periodic table and looking up what thing has atomic number 86, that would be Rn, radon. Another example, oxygen-16 will undergo beta decay, beta minus decay. Remember that the beta minus particle, the electron, has an atomic number of -1, and it's got a mass number of 0. And so the atomic number, the mass number of our product has to be 16, and then 8 plus -1 would give you 9. It's going to be 8 minus -1, would give you 9 for the atomic number. And so looking at the periodic table, the thing that's got atomic number 9 would be fluorine. One more example. Suppose I wrote something like this. Like bismuth-213 undergoes alpha decay. It'd probably be more meaningful to write it like this. Like write it as helium-24. We're expected to know what an alpha particle is, in other words. And so we can, again, balance the atomic number, balance the mass number. And we would get 81 for the atomic number, 209 for the mass number. And looking that up, that would be tellurium on the periodic table. Okay, so that's all the new information for today. Real quick pop quiz. Of these three things, which one is the most radioactive? If you picked the banana, you're absolutely correct. Bananas are actually pretty radioactive because they contain an isotope of potassium called potassium-40. And you actually see this isotope in lots of different food items. And so of all these things, bananas are the most radioactive. But it's not radioactive enough for you to worry about. That's very, very small amount of radioactivity. So most things that are radioactive in our everyday lives produce a very, 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 very minimal amount of radiation. In fact, it's about equal to all the things in your life combined to the radiation that we get from the Earth itself and the background radiation from the sun and other things outside our atmosphere. And so even though I say bananas are radioactive, they're really not going to hurt you. So, the end for now. Ta-ta.